Hello! It's the moment you've been waiting for. Your next stats note video. This is so exciting. I can't wait to get started. All right, so what are we doing today? We're still looking at confidence intervals. We're going to start with proportions, which is kind of where we finished last notes. And then we're going to move on and talk about some of the extra complications that involve doing confidence intervals with means that I sort of alluded to last video, but we didn't get into. So quick recap about sampling distributions for proportions. We've seen this again and again and again, but they're still going to be relevant to what we're doing today. All right, so randomization independence, 10% when sampling without replacement, and 10 successes, 10 failures. All right. This is sampling without replacement. All right, and I know I keep putting this on here, but they're important, so I'm just going to keep driving it home by putting it on again and again and again and again. All right, margin of error. We talked about this last note video. What we're going to do is we're just going to put down kind of a formula for margin of error, because that formula is going to be useful when we do these sample size problems that are right below. All right, so what's the formula going to be? And first, what's the definition going to be? So the distance from the point estimator to the end of each interval which is what we saw last time, and we can find that using this formula. Margin of error equals Z star times PQ over N, which again is the standard deviation of our sampling distribution. So here we have standard deviation. Here we have a critical value. All right. And this formula is going to be useful for us when we're looking at these sample size type problems that are right below. So it says, choosing your sample size. Sometimes the questions you will ask how large of a sample you would need to create a confidence interval with a certain margin of error. All right, so like you're trying to, predict an election within 1 or 2 percentage points. How many people do you need to talk to have that level of accuracy and still be 95% confident that your interval is going to contain the right value? How many people do you need to talk to if you want to be within 0.5%? How many people do you want to talk to if you need to be within 0.75%? But, if you want a specific margin of error, how do we calculate the size sample that we need to get that result? All right, so this question says, if a candidate is planning to poll an estimate planning a poll to estimate voter support within 3% with 95% confidence, how large of a sample does she need? All right, so we're basically going to use this formula and plug in the different pieces. So our formula is margin of error equals Z star times PQ over N. Now, the margin of error is given to us in the problem. Right? It says within 3%. This is our margin of error. All right, so that's the first piece we can plug in, 0.03. All right, the next piece is Z star. All right, well, we can get that based off of this information right here. All right, it tells us we need to be 95% confident. So that means Z star is calculated by doing an inverse norm of 0.025. Now, why is it 0.025? Because again, that's looking at the middle 95%. There's 5% left over, but that 5% is split between the left side and the right side. Now, again, this is going to give us a negative value, but technically we always use the positive. All right, so even though this is going to give us a negative value, we're going to use the positive version of this. Now, P and Q, the problem doesn't give us. But look at this little bubble here. Since we don't know voter support, we will use the worst case scenario, which is P of 0.5. right, now why is 0.5 the worst case scenario? Well, I can show that really quickly on my calculator. All right, if I use 0.5 as p, then I'm multiplying it by 0.5, which gives me 0.25. Let's pretend p was 0.49. That would make q 0.51. Notice that that number is smaller. All right, let's say p was 0.51. That would make q 0.49. The number is smaller. It doesn't matter what I put in here. Any combination that's not 0.5, 0.5 is going to be smaller than that 0.25 that I got. All right, so when we don't have any information, we use 0.5 and 0.5 because that's sort of the worst case scenario. So this is going to be 0.5 times 0.5. And then the n is what we're actually solving for. Okay. Now we have an equation. We just have to go through the algebra to get n. So this is going to be 0.03. Again, this is going to give us a negative 1.96, but we're going to change that to positive 1.96. All right, and then we have to kind of solve this right here. Now, I could just as easily rewrite this fraction as 0.5 times 0.5 over the square root of n. Right? Those are the same exact things. And if I take the square root of 0.5 times 0.5, it's going to be 0.5. All right, so the square root of 0.5 times 0.5, because that's basically 0.5 squared. And if I take the square root of it, it's going to send me right back to 0.5. So I'm left with 0.03 equals 1.96, 0.5 over the square root of n. All right, and then again, I just have to keep going through the algebra here. So I could multiply 1.96 and 0.5. So 1.96 times 0.5 is going to be 0.98. So now I've got 0.03 equals 0.98 over the square root of n. All right. Multiply both sides by the square root of n, and I get 0.03 square root of n equals 0.98. Divide both sides by 0.03. All right, 0.98 divided by 0.03 is going to give us 32.67. And then if I square both sides, I can get n equals, let me square this, 1067.11. But when we're doing this type of problem, we're always going to round up, because technically if we only talk to 1,067 people, our error would be a little over 3%, and we'd rather always have it be a little under 3% than a little over 3%. So our final answer would be 1,068 people. All right. So kind of building off what we did last class, but using it in a different way to, answer a different question. All right, so let's try another one of these just to sort of get used to them. Starting a nightclub. A college student organization wants to start a nightclub for students under the age of 21. To assess support for this proposal, they will select an SRS of students and ask each respondent if he or she would patronize this type of establishment. They expect about a 70% of the student body would respond favorably. What sample is required to obtain a 90% confidence interval with approximate margin of error of 0.04? So again, margin of error equals Z star times PQ over N. All right. Now, kind of going through our problem, margin of error is given to us. All right. Confidence interval, we're going to have to feed into an inverse norm, but that's how we're going to get our Z star. And then this problem gives us an expected P. So instead of using 0.5, 0.5, which is the worst case scenario, this is going to be what we're going to use as our P, because the problem gives us a value. So we don't have to go with worst case scenario. We can say, all right, if they're expecting about 70%, we'll use that as our P instead of 0.5 and 0.5. All right, but then it's just plugging things in. So 0.04 goes in for my margin of error. All right, Z star is going to be the inverse norm. 90% means there's 10% left over, but it's split between the left and the right. So that's 5%. And then this time our square root is 0.7 times 0.3, because P and Q always add up to 1, divided by N. All right, we've got all the pieces. Now it's just a question of going through and doing it. So the first step is probably to do inverse norm. So inverse norm of 0.05, again, gives us negative 1.64, but we ignore the negative. We're just going to use positive. So we're left with 0.04 equals 1.64 times the square root of 0.7 times 0.3 over the square root of n. Now, again, you can kind of rewrite this different ways, but I'm going to rewrite it as 0.04 equals 1.64 times 0.7 times 0.3 under a square root. And then that's all divided by the square root of n. All right, so this top, these are all numbers, so I can just do that on the calculator. 1.64 times the square root of 0.7 times 0.3. 7515, we'll say. All right, so if I go up here, I've got 0.04 equals 0.7515 over the square root of n. Multiply both sides by the square root of n equals 7515. Divide both sides by 0.04. And again, I'm just doing it right in my calculator. So even though I wrote the rounded version, I'm using the full version on my calculator. As typical, I'm not going to get too hung up on rounding as long as your numbers check out. That's all I'm concerned about. We'll write 18.7886. And then I'm going to square both sides to get rid of that square root. And again, I'm just keeping it all in my calculator here. But this gives me 353.01. But again, if I round down, technically the margin of error becomes a little bigger than 4%. So I'm going to round up and say that's 354 people. All right, but that's what these problems look like. So that is one type that you're going to have to be able to do in here, where they give you this information, you're using this formula, and you're calculating a sample size from that. All right, and this is a calculation that people need to do when they're actually performing research and designing their studies, is they establish what they're willing to tolerate, and then they kind of work backwards and say, all right, if we're willing to tolerate this, we have to talk to this many people. This is what it's going to cost us. Is that in our budget, et cetera, et cetera. Again, when they give you a P, you can use that in your formula. When they don't give you a P, you use the worst case scenario, which is 0.5. All right, coral reefs. All right, we're going to do one more confidence interval together. This is sort of what we did last class, but I think it's worth going through the process one more time before we move on to sort of new stuff. So coral reef communities are being destroyed in part by a disease called aspergillosis. Scientists found that 54 of 104 sea fans sampled were infected with that disease. We can say, what can we say about the true proportion of sea fans that are infected? That is, determine a 95% confidence interval. After you create the confidence interval, state your conclusion and interpret what it really means. All right, so this is like a typical confidence interval question. So going back to kind of last class's notes, to do a confidence interval, we need a critical value. which is our Z star, and we get that based off the desire for a 95% confidence interval. So 95% confidence interval means you've got 5% left over, or 2.5% on each side. So we're doing an inverse norm of 0.025, which we actually just did on the front here. So we already know that that's going to be 1.96. All right. We also need a standard deviation. All right. And a standard deviation involves knowing your P. So where's the P in this problem? Because I don't see a percentage anywhere. Well, the P is right here. Found that 54 of 104 were sampled. All right. So we're actually going to have to calculate P hat ourselves. All right. So I'm going to go over here and say P hat is 54 out of 104. All right. So 54 divided by 104 is 0.5192. All right. We know that Q hat is equal to 1 minus P hat. We know that P hat is 0.5192. So that means that Q hat is going to be 1 minus that, or 0.4808. Because the two of those together will add up to 1. All right. Now that we have our P and the Q, we can go over here and say, all right, our standard deviation is P hat Q hat, because we're dealing with a sample here, over N, or 0.5192 times 0.4808 divided by our sample size, which was 104. All right. Again, that's from our problem, but that's our N. All right. And when we do that on the calculator, 0.5192 times 0.4808, divide that by 104, and then take the standard square root of that, we get a standard deviation of 0490, basically, 0490. So we'll say 0.0490 when we round that. All right. So that means our margin of error is going to be equal to the critical value, 1.96, times that standard deviation that we just calculated, which was 0490. So 1.96 times 0.0490, 09604. All right, 0.09604, which means our confidence interval which is the point estimate, kind of just dragging up the vocab from last class, plus or minus the margin of error. Well, our point estimate is what we got from the sample, so that's 0.5192. And then we're going to plus and minus the margin of error, which we just calculated to be 09604. Which gives us an interval from, let's see, 0.5192 minus 0.09604. We'll say 4232. 4232, 2, and then let's see, 0.5192 plus 0.09604, 6152. So the sentence we would generally write is, we are 95% confident the population parameter is between 0.4232 and 0.6152. All right. And again, that 95% confident is basically saying, hey, if we did this process over and over and over again, 95% of the time, we would end up with an interval that contains the true value. Right? Not every time. 5% of the time we wouldn't, but 95% of the time, we would get an interval that contains the true value. Now, you're about to hate me, at least a little bit, or you're about to love me. I don't really know how it goes. But this is how confidence intervals are created. All right, this is the process that we go through to actually come up with these numbers. Going forward, you are allowed to use your calculator to create the confidence interval for you. I wanted you to see the process. I wanted you to know where it was coming from. When you're reproducing this on a test or a homework, you are allowed to use the calculator. And you're going to see that it makes it very, very easy. So where do we go on the calculator? All right, we go to Stat. All right, so the Stat button, and then we scroll over to Tests. And this is Test menu is where we're going to be spending most of the rest of the year. So what we just created was a 1 proportion Z interval. All right. We're not doing tests yet. So anything that says test, you can ignore for right now. All right, that's the next unit. We're down here in this interval section. All right, we had 1 proportion. All right, we only had 1 percentage. So we're making our interval from that 1 percentage. So again, this is 1 prop Z int is the one that we're choosing. And then in there, it's going to ask for a few things. So X is your number of successes. Well, the problem told us that there were 54. So our number of successes would be 54. N would be your sample size, just like it always is. All right, so our sample size was 104. So we can type in the 104. And then the confidence level for this problem was 95%. So I can type that in as 0.95. So I have 54 successes out of 104 trials. My confidence level is 95%. When I hit calculate, it's going to give me an interval, and it's going to say that the interval is 4232, which is what we got, to 615. Technically, that would round up to 3. That's what happens when you're rounding a whole bunch. But it's giving us that same interval. And that 5192 is the point estimate. That's the center of your interval. All right. So this is going to be an acceptable way of doing the problems on quizzes and tests. All right. All you would have to do is tell me that you are doing a 1 prop Z interval so that I know which one you picked. You would have to tell me what you used as your X. So in this case, 54. You would have to tell me what you used for your N, in this case, 104. And you'd have to tell me what you used as your confidence level. And in this case, it was 0.95. And then that suffices as your work for the eventual interval that it spits out, which was 0.42321 to 0.61525. Okay. So you do not have to go through and do the long by hand process. I wanted you to see it. I wanted to practice it a few times so that you would know where these were coming from. But let's let the calculator actually create it for us because it's going to be more accurate. All right. We're rounding and we're losing some accuracy here. There's lots of places where we can make mistakes. As long as we type the numbers incorrectly, the calculator is going to get us the right interval every time. All right. So we're going to use that going forward. So I don't know whether you love me because this is way easier or if you hate me because I made you write down all of this 2 seconds earlier. It could go either way, really. All right, so we've done enough with proportions now. Let's go back to population means. All right, so here's that same box, but for population. So again, randomized independence, 10%, your sample has to be 100% of the population when sampling without replacement. All right. And then we need a large enough sample. All right, this is going back to the central limit theorem, which as long as n is greater than or equal to 30, it doesn't matter what our population is, the sampling distribution will be normal. Or if your original population is normal, you're fine. So this n is greater than or equal to 30 is only necessary if the population is not normal. All right, but we've got all this other stuff. The mean, this didn't print out right. The mean of the sampling distribution is equal to the true mean, and then the standard deviation of the sampling distribution is equal to the standard deviation divided by the square root of n. All right, so I did say last class there was going to be some extra wrinkles here. And the wrinkle is that there's actually two different procedures for these confidence intervals. One is where you know the population standard deviation, which is what actually happened in the notes from last class, right? When we did the whole little mystery mean where the magic number was 244, I gave you a population standard deviation of 20. I said, all right, your population standard deviation is 20, right? There's a second procedure when we don't know the population standard deviation. Now, this first one that we did last class is really mostly theoretical, because how are you actually going to know the population standard deviation? You're probably not. So you're really not going to be able to do it. This one is the more practical one. So this is the one that we're going to actually be focusing on for the rest of these notes, because it's the most common. Now, before we get into that, I do want to show you one more problem about calculating sample size, just so you can see how it would be different for one of these scenarios when we're dealing with means as opposed to proportions. So this one says administrators want to estimate how much time students spend on homework on average during a typical week. They want to estimate mu, the true population parameter, at a 90% confidence level with a margin of error of at most 15 minutes. A pilot study indicated that the standard deviation of time spent on homework per week is about 154 minutes. How many students need to be surveyed to estimate a margin of error of at most 15 minutes? So pretty much the same problem as before. It's just the formula has shifted a little bit. All right, so instead of using PQ over N, we're saying, okay, the margin of error is equal to Z star, and then we're using the formula that we have for this standard deviation of a sampling distribution for means, this one up here. Otherwise, the problem is exactly the same. So it tells us the margin of error is 15 minutes. So that's going to plug in for our ME. All right, so ME is going to be 15. All right, Z star we get from the fact that they want a 90% confidence level. So this is going to be able to inform what we need to do for Z star, and that's inverse norm of 0.05. Again, 90% confidence means there's 10% left over, but it's split between the left and the right. All right, the problem gives us the standard deviation. All right, it says the standard deviation is about 154. So there's our standard deviation. And then we're solving for n. That's what we want to know. So if anything, these versions are just easier because you don't have like a radical with a bunch of decimals underneath it. It's a little more straightforward. So again, inverse norm of 5%. It's going to give us a negative 1.64, and we're just going to use the positive version of that. So we're going to use the positive 1.64. So we've got 15 equals 1.64 times 154 over the square root of n. So again, 1.64 times 154 gives us 15 equals 252.56 over the square root of n. Multiply both sides by the square root of n. Divide both sides by 15. Divide by 15 equals 16.8373. I'm just going to keep it all in my calculator here, and then I'm going to square both sides. And we get 283.4958. 283.4958. And even though technically that would round down, rounding down would make our margin of error slightly larger than 15 minutes. So if we're going to round, we want to make it at least a little less than 15 minutes. So we would just say 284 people. All right. So again, I just wanted you to see one of these using the other formula. It's exactly the same as what we just did. In fact, it's easier. You're just using, instead of PQ over N, you're using the standard deviation divided by the square root of N. All right, so you can see these types of sample size problems in either flavor. Doesn't really matter which one. You just have to plug in a different formula and go from there. All right, so population standard deviation is unknown. This is sort of the real world scenario. You're sampling from a population, you calculate a mean, you don't know the population standard deviation. You might know a sample standard deviation, but you don't know a population standard deviation. So what do we do? All right. Well, to explain what we do, we need to talk about something called the t distribution. All right. So just like proportions, if you don't have the population standard deviation, you can use the sample standard deviation. All right. That's what we were doing here. All right. When we didn't know the population standard deviation, we used the sample P and Q. All right. So that's what we could do. However, when the sample size changes, the distribution changes. All right. So we're not going to be using the normal distribution when we do this. We're going to be using something called the t distribution. Now, the t distribution is very similar to the normal distribution. And as your sample size increases, the t distribution gets closer and closer to the normal distribution. So if your sample is sufficiently large, it's pretty much going to give you the same answer whether you use normal or t. But technically, we always use the t distribution. So what is it? What does it look like? How is it different? All right, let's start with a graph of the normal distribution. So if you go to y equals and you go to your distribution menu and do normal PDF. All right, if you put in the x value as x and 0 and 1, that will actually allow you to graph the normal distribution, which is what I've done here. All right, I've put the normal PDF in x, 0, and 1. Again, this isn't anything I'm going to ask you to do. It's just for our demonstration purposes. Now, if I hit my graph button, you're going to see that there's my normal curve. All right, so I'm going to sketch that on my sheet here. And I'm going to be like, all right, here's my normal curve. It goes down, and it's got these really sort of narrow tails. But there's my bell curve. Whoa. That's an awkward graph. This side looked really good. This slide, my pen sort of slipped. I apologize for that. Doesn't look as good. But this is my normal curve. Hopefully your two sides are a little more balanced than this awful side that I just drew right here. Let's just focus on this side. This is the good side. All right, so now let's look at a t distribution. All right, so what I'm going to do is I'm going to go back into my y equals. I'm going to go down to y2. And instead of doing normal CDF, I'm still going to go to that distribution menu. And I'm going to go to t PDF. Right? I'm still going to put in x as my x value. And then the t needs something called degrees of freedom, which is basically the sample size minus 1. So I'm going to start with a really tiny sample. Let's just pretend my sample had only 2 people in it, which means my degrees of freedom would be 1. All right, I'm going to paste that in there, and then let's look at the graph. So it's drawing that t-distribution right now, and hopefully what you notice is it's not going up as high, and the tails are fatter. There's more area in the tails. All right, remember, the area underneath the curve corresponds to percentages. So there's more area out to the extremes of the curve. All right, so let me draw that in here. Let's see if I can do a little better this time. So there's this one. And then this one gets a little goofed up now because the first one was so poor. But basically, right here, I have a t-distribution with n equal to 2, which means degrees of freedom is equal to 1. All right. Now, why are the tails wider? Why are the tails fatter on a t-distribution? It's to account for the extra uncertainty. All right. We don't know the population standard deviation. We're using the sample standard deviation, which means there's a chance that we're off. All right. When we calculate our standard deviation from a sample, we're doing our best, but it doesn't mean we got it right. I mean, we've seen that time and time again with our samples. You don't always get it right. So we've introduced this extra level of uncertainty. And to compensate for that, we allow more extreme values to have a higher probability. Because we're saying, all right, there's all this extra uncertainty. Maybe our standard deviation's right. Maybe it's wrong. Maybe it's too low. Maybe it's too high. But to account for this extra uncertainty, we're going to put more area out to the extremes of the distribution to account for that extra uncertainty. All right, now watch what happens when our sample size increases. So I'm going to go back to y equals. I'm going to go to t-PDF again, x, and I'm going to jump my degrees of freedom up to 9, which means my sample is actually 10. All right. When I graph that one, all right, it's drawn that line there. You're seeing it's a lot closer to that normal curve. All right. Still not on the normal curve, but we're getting a lot closer to that original normal curve as our sample size is increasing. So we've got this third one in here. It gets a lot closer to the normal curve. So again, this would be a t-distribution with n equal to 10, which means the degrees of freedom were equal to 9. All right. So the general kind of point of doing this is to just understand that the t-distribution has fatter tails, and the implication of that is more extreme results, meaning further from the center, have a higher probability of occurring. And again, that's to kind of offset for this extra uncertainty that we have. All right, so let's get some definitions down, and then we'll see how this actually sort of plays out with some calculations and some problems. So T-model is a family of distributions indexed by its degrees of freedom. Right? And basically, these are used for the inference of means, trying to figure out what the mean actually is. All right. And then degrees of freedom, All right, the reason we do this is, and again, you don't need to know the exact definition of degrees of freedom. That's kind of above an introductory. You don't need to understand the entire concept of degrees of freedom. That's kind of beyond an introductory stats course. But what you need to know is when working with means, we need to adjust the normal model, which is what we're doing with the t-distribution, based on sample size. And degrees of freedom is equal to n minus 1. All right, so it's kind of a proxy for sample size, but it's one less than the sample size. All right. Now, let's see how we actually sort of kind of create confidence intervals with this. So it's still the same general formula. All right, we still have our point estimate. We still have a critical value. And we still have a standard deviation. So what's different? Well, we've traded out Z star for T star because it's going to be a T distribution. And we've traded out the population standard deviation for a sample standard deviation. Now, right here are some instructions on how you can find a critical value on a TI-83. I'm not sure anybody still has a TI-83, but they're on there just in case. Chances are you can ignore that and you don't need to worry about this. But if you do have a TI-83, then that might be relevant to you. All right. So how do we find a critical value using TI-84 or above? So your calculator has an inverse t function in the distribution menu. It works exactly like inverse norm, except you also have to provide the degrees of freedom as the second argument. All right, so let's pretend that we needed to calculate a t star, and I wanted to do it for a confidence level of 95%. And we'll say that our sample was size 5, which then implies that our degrees of freedom would be 4. All right. So to do that, we would go to our distribution menu. We would go to inverse t. We would say, okay, 95%, but that's split between the left and the right. So 2.5% on one side, 2.5 on the other. And then my degrees of freedom would be 4. And that gives me, 2.776. Again, we're going to ignore the negative. So let's just say inverse t. Now it's not inverse norm, it's inverse t of 0.025 when there are 4 degrees of freedom equals 2.78. Now, compare that to inverse norm. Of 0.025. That's the 1.96 that we're used to. All right, so this is larger to account for the extra uncertainty. So our intervals are going to be a little bit larger to account for that extra uncertainty. All right, so let's practice this just a couple of times here. Find the critical value for a t-distribution with 80% confidence and 11 degrees of freedom. So 11 degrees of freedom means our sample size is 12. All right, not really relevant for this question, but it's good to always think about that just to keep them straight in your head. So we would do an inverse t. 80% means there's 20% left over that's split between the left and the right. And we need 11 degrees of freedom. So again, inverse t instead of inverse norm, we're changing that to 0.10, and we're giving it 11 degrees of freedom. And that gives us 1.36 because we ignore the negative. Same thing down here. Find a t distribution with 99% confidence and 7 degrees of freedom. So 7 degrees of freedom means our sample size is 8. We've got a 99% confidence. So again, distribution inverse t. 99 means there's 1% left over, but it's split between the left and the right. So that's 0.005, 0.5%, with 7 degrees of freedom. All right, and that one works out to be 3.50. All right, so inverse t of 0.005 with 7 degrees of freedom equals 3.50. All right, and again, these are t stars. There are critical values that we're going to use when creating our confidence intervals. So these are our t stars versus inverse norm, which gives us a z star, because that one's based on the normal distribution. All right, so now that we know how to find t star, we can find a confidence interval the same way we did with proportions. All right, a major pollutant in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides. Researchers collected data on NOx levels for a random sample of 40 light-duty engines of the same type. The mean NOx rating was 1.2675, and the sample standard deviation was 0.332. Construct and interpret a 95% confidence interval from the mean amount of NOx emitted by these engines. All right, so it's a good idea to just kind of think through your conditions. So random sample, we've got that. 10%, we don't know whether this is more than 10% of the population, but it seems likely that it's not, so we're fine there. Large enough sample, right? If it had told us the population was normal, we wouldn't care. But since it doesn't tell us that, we know that n has to be greater than or equal to 30, and it is, so we don't care what the population looks like. All right, we know that our sampling distribution will be normal regardless. All right, so now that those are in place, we can actually calculate our interval. And we're going to use x bar plus or minus t star times the standard deviation of x over the square root of n. All right, it's the same thing we did with proportions. All right, we need a critical value. This time our critical value is coming from inverse t. We want a 95% confidence level. So that means we're doing 0.025. Now, if our n is 40, that means our degrees of freedom is 39. So we're going to do 0.025 with a 39 there. All right, so inverse t, 0.025, 39 degrees of freedom. Again, we ignore the negative, so this is basically 2.02. All right, we need our standard deviation, which we're getting from our sample standard deviation. All right, they don't give us the population standard deviation, so we're stuck using the sample standard deviation, which is why we're using t instead of z. All right, and then we have the square root of our sample size right here, which the problem told us was 40. So this is going to work out to be 0.3332 divided by the square root of 40. So 0.0527. All right. So that means our margin of error is equal to the 2.02 times the 0.0527. 2.02 times 0.0527, or we'll say 1.1065. All right, and then our confidence interval is just going to be our point estimate, which is the 1.2675, plus or minus our margin of error, which was 0.1065, which gives us an interval from 1.2675 plus 0.1065, 1.374 on the high side. And if we have 1.2675 minus 0.1065, we end up with 1.161 on the low side. 1.161. So, we are 95% confident. We are 95% confident. The population mean is between 1.161 and 1.374. So same premise, same style, just different formula and different distribution. But the mechanics, the main gist of it stays exactly the same. Now, again, just like proportions, I'm showing you where these numbers are coming from. We're actually going to do it generally on the calculator. So again, if we go back to stat, tests, all right, we are going to be using the T interval. All right, Z interval is if you know the population standard deviation. We don't ever know the population standard deviation. So no question for me will ever be using Z interval. All right, if you're doing a question for me, it's going to be using the T interval because you don't know the population standard deviation. How are you going to find it out? How do you know the population standard deviation without knowing the population mean? Doesn't make any sense. So we're always going to be using T interval for these. Now, with the T interval, you can either use data or stats, right? If I were to give you raw data, you just tell me what list the data is in, you tell me the confidence level, and it will do the rest of the work for you, right? If you're going with stats, you have to type in the mean, which for this problem was 1.2675. You have to tell me the standard deviation, which for this problem was 0.332. You have to tell me the sample size, which for this problem was 40, and then the confidence level of 95%. It will take care of the rest. It'll use the T distribution. It'll do the correct degrees of freedom. It'll get you everything that you need to do. And you'll see, again, we're getting slightly different answers because of rounding, but 1.1609 would round up to 1.161. And 1.3741 would round down to 1.374. So we're effectively getting the same answer. And again, on a quiz, on a test, on a practice or a warm-up, you can just write your work as, okay, I did the T interval. I specified my X bar as 1.2675. I specified my S of X as 0.3332. I specified my N as 40, and I specified my confidence level as 95%. All right, and that would be enough work. And then your answer would just be the 1.1609 to the 1.3741. All right, and that's fine. Like, you can solve your problems by showing me this. I don't need you to do it out the long way. I want you to understand where it's coming from. I want you to understand what this is, but this is perfectly acceptable as work for generating one of these. Okay? Now, the Environmental Protection Agency sets a limit of 1 gram for NOx emissions. Are you convinced that this type of engine has a mean NOx of 1.0 or less? All right. No. All right. Because our interval was entirely above 1. So no, because 1.0 is not contained in our interval. All right. 1.0 is below our interval. Suggesting the true value is higher. All right, so that's just making sure that you kind of understand what this interval is really showing and kind of interpreting it and using it to answer some various questions. All right, so that's it. Kind of like a quick recap here. We've got these questions where you're figuring out sample size. And again, for that, you're using the margin of error formula. Now, when it's proportions, you're using ME equals Z star PQ over N. Z star is coming from inverse norm, right? When it's means, you're using ME equals Z star and then standard deviation divided by the square root of N. All right, same thing, you're kind of plugging things in, solving for the number of people, right? When you're doing confidence intervals, if you still always need the same information, you need critical values, you need standard deviations, you need margin of errors, you need your point estimate, and then you're putting those all together to get the intervals, but you can use your calculator. With populations, all right, we switch over to the t-distribution to account for the extra uncertainty of not knowing the population standard deviation. And the main difference between the t-distribution and the normal distribution is that the t-distribution has fatter tails or more area at the extreme portions, which makes it more likely that you're going to get really low or really high results. And it kind of shifts the probability in those directions. But then the process of kind of calculating the confidence interval is exactly the same. You have a point estimate, you have a critical value, you have a standard deviation. These two things together form your margin of error. And we can either do that by hand, like we did just here, or we can do it on the calculator using t-interval. All right. Never use z-interval. All right, that's when you have the population standard deviation, which really doesn't make sense. You're not really ever going to have that. You know, the only time you have that is like in an imaginary problem where I give it to you. All right, and I'm not going to give you any of those. I'm going to give you t-interval type problems. All right, so as usual, if you have any questions, let me know. Otherwise, have a great day, and we'll see you later.